So, yeah, again, good morning and welcome to the data science class, Osiri University. So, this is week number 5, but let me do a quick recap of week number 4, and I hope every one of us has been tracking. We talked about, you know, predictive modeling, which is the grand topic, right? Which we'll be focusing on in week 4 and then week 5. So generally, we're talking of predictive modeling. So one of the things we did was actually define or explain what predictive modeling is, which is the process of using data and statistical learning techniques rather, to forecast or estimate future outcomes based on historical or current data. So we're essentially picking up existing data and using it to develop models that can help us forecast the future. That's what you do with predictive modeling. We talked about why predictive modeling matters and then how it works, the various steps. You define your problem, because some people just go straight to doing you know the technical things, right? Quote and unquote, the technical things, without recourse to the reason why this project is being done. It's always, and you're not an effective data analyst if you do not understand subject matter issues, or at the very least, you do not have a subject matter expert, right? That really understands the domain you're working in. So, which is why problem definition, is really very important. I would say if you're able to um, properly define or articulate a problem, you probably have done 40% of the work. And then things like data, being able to get the data, clean up the data, and position that data very well, you probably have done another 30% of the work. Modeling might be like 20%, and then explaining what you have done, storytelling is the rest of it, which is 10%. That's not to say that that 10%, right, is not important, but it does say that there are a lot of really important things. And the hope is that you are already skilled in the art of being able to tell your stories. Because if you do all your good work and you're not able to tell your story and communicate the results, you would have failed woefully anyway. All right. So, um, we talked about, all of those things, uh, problem definition, data collection, pre-processing, feature engineering. And last week, I kind of tried to help us understand what features are. When we talked about, I gave us an example of house sizes and house prices. And then we had a situation where you had multiple features, right, that could determine house prices, right? And how each of those features, which is typically what you see on the column of, for example, an Excel sheet, right? All of those are your features, the individual characteristics that help predict the price of the house. So the subject of feature engineering is a whole discipline of its own, because here it talks about the creation, selection, and transformation of variables. Sometimes you need to transform some of those. Where we talked about encoding, and we talked about one-hot encoding and all of that. So what I would encourage is pick a pen, a paper. If there are terms that do come up, write them down if there are terms you're not familiar with, and just do some additional research on them. So we talked about the model selection, and there are different kinds of models. And what we're going to do today is continue with some of those models that are available for predictive analytics or modeling. And here we mention linear regression, decision tree. We're going to touch a little bit on decision tree today. There is forest drive, XGBoost, neural networks, and on and on. There are so many models, and then some of those models have different variants of of same models. So being a good data analyst or good, I would say, data scientist or machine learning, you know, scientist, right, or data engineer would ride a lot on being able to know what the various models are and what they do, and to be able to create a discrimination between the various models, how they compare and how they are different, and in what areas they are best applied. So model training, of course, which is when you feed the model, and then evaluation, very, very, very important. And then last week we talked about the different kinds of evaluation methods, the RMSE, MAE. We haven't talked about accuracy is the general accuracy thing in the most part. We haven't talked about F1 score. I think if we have time today, we're going to go into F1 score and AUROC, because then we'll begin to talk about precision, we'll talk about recall, and all of the other things that are involved. And again, if we are unable to um, get to those points, I would have videos on all of those posted for you, though it might be helpful to do at least an overview so that we can understand how all of these plays out and where each of them falls in the equation. But generally, you need to be able to evaluate your model to be sure that the results you're actually getting do make sense. And of course, the other area is deployment. This is a whole discipline all by itself. After you get those models, you have to deploy them somewhere, and then you have to model and update them, because sometimes when the data that you were used, right, the circumstances under which the data that you were used to build a model, when those circumstances change, the prior data might not, be able, when you run inferences on current situations, which is the change situation, and you're using models that were developed based on data from completely different situations, you're going to all of a sudden begin to get errors. So, which is why you need to constantly monitor, the environment. That it could be your marketing environment, it could be any kind of environment, right? That the new data that is being captured, or the circumstances rather, that those circumstances are the same. Because if they are not the same, all of a sudden you're going to see that your model is going to be predicting unusual errors, and then that's where you want to capture data from the new circumstances, feed it back into the model, retrain the model, so that you can, when you do your inferences, you can get better outcomes. So, which is the area of monitoring and updating. So, there's nothing like I've gotten a data scientist, they've built my model, and then they are off on their way. Nothing like that does exist, because data is very dynamic, which means your models are going to be very dynamic, if you're going to keep abreast of the situations within the environment that you are measuring. So types of predictive maintenance and modeling. Talked about regression, classification, time series forecasting, and survival analysis. We really didn't talk about survival analysis much or at all here. Our primary focus for this course is going to be three of this, right? Time series, I think we have a whole week that is dedicated to time series, but regression and classification will be the main focus of week 4 and 5. So we talked about regression, what it is. We talked about supervised learning and unsupervised learning. Then we talked about regression, a type of supervised learning. And then, of course, we went into classification, and what else? I think that's probably, and then we're able to go through a couple of codes to help us get a better understanding of what's going on with all of those. So I tend to focus on these slides because I know most other material, you can get them anywhere. You can get them on YouTube, you can get them anywhere. But this will be a very good reference for you to be able to actually do implementation of whatever the models are, or whatever techniques. You can see how it's modeled. You can see the errors, like your R squared, your mean square error, all of that. Everything is captured in the slides. Questions? Um, questions? No questions for now. Okay. So I'm going to slide into week 5. Um, Sorry, this is week, and sorry I haven't posted week 5 slides yet. I would post them right after this class, and then I will check on what yeah, Vicky, please go ahead.
Thank you, sir.
Yeah.
So do you mind going through very quickly, like the different errors? I don't think I still get it.
Okay, yeah, that's fine. That's fine. That's fine. That's fine. Let me
Thank you, sir.
yeah, not a problem. Let me see if it was here that we talked about it. Yeah. 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 So I think this is where we talked about the different kinds of error. Let me see. Let me just check one more thing, and because I'm trying to see where we did an actual implementation of it. And then I can use that to explain. Okay. I don't think it's here. It's probably the other slide we used, and I'm going to pull it up and I will discuss it later. But let me go back and see. Just 1 minute. I'm trying to see the one I was trying to. So yeah, so this is your mean absolute error, right? So if you can see here, I don't know if you can see what's going on here, right? This is a summation of, let's assume you have say 10 different observations, right? The mean of those observations, for example, which is like, let's say I have 10 observations, 10, 10, 10, 10 in, that's just to keep it very simple and easy, right? 10, 10, 10. Let's say we have 5 tenths, right? Which is 50, right? So the average of 50 is going to be something like 50, right? And what I want to do is each of the observations, I do each of the observations, or let's look for something that's so that nobody gets confused. Let me look for something. Let me say 23 plus 45 plus 78 plus 90, which is how many observations? 1, 2, 3, 4 plus 100, right? 336. 336. And how many of them? 1, 2, 3, 4, 5 divided by 5, right? That's my mean right here, right? So when I come here, right, 67.2 is my average. So that will be my y hat, right? And then you have my y1 minus y hat. So each of this is your y1, y2, y3, y4, right? When you come here, so what you have here is, for example, starting with 23, it will be 23 minus your average, right? And you do that for each of them, right? And then you divide the answers you get. So it will be something like y1 minus the mean, right? Plus y2 minus the mean, plus y3 minus the mean. And then you do that up to the fifth one. And then you divide everything by the number of observations, right? That way, that's how you get your mean absolute error. And then you have your MSE, which is your mean squared error. Now, instead of just having y1 minus y hat, which is your mean, now what you're doing is you're actually squaring it, right? Remember in the first case, we had our 23 minus 60 something. Then what that led to is us having minus values, right? But in this case, what you're doing is you want to eliminate those negatives, right? And you're squaring everything. And that's why it's called your mean squared error. But one of the things it does is that it actually penalizes large errors. So, which is, for example, if you have, and sorry, the other thing I didn't mention is when you are doing your y1 minus y1 hat, what you are actually doing is you're looking for the error, the difference. So what that means is if you have a large difference, right, then when you square that large difference, then all of a sudden is the error is exaggerated. And then you have a situation where you take the square root of this, you know, and then so different things. You can also see this particular one where what you're actually doing is you're looking at the variance, the residual variance divided by the total variance, and then you subtract it from one, right? So those are different. But in actual summary, those are the different errors, and then the part you would want to go do, and I think we ran through some of that in the multiple choice questions, is you trying to understand at what point do you use each of the errors and why, and what story are they actually trying to tell you. So at the risk of spending all of our time in on this topic, because we have a whole lot going on today, that would be the general analysis. And I think I did put a couple of videos for last week that actually drills down to explain what each of those errors are. And then here you can actually then go ahead and implement the error, which we showed here. You can see your R2 score, your mean squared error, all of those are included here. Again, remember I mentioned that now you don't have to write out all of the formula in Python because there are methods that already exist, that help you do these things in the background. All you have to do is declare your data, so like your Y, you already have your Y here, right? And then this is your predicted value, because at the end of the day, you're going to predict some kind of value. This is your predicted value. So you have your value and then your predicted value, right? And then you can now look for the mean of you can do the R2 score and then you can do the score. And in this particular place, what's happening is you have your Y and then the predicted Y, right? So that's the other one. Oh, there's something I missed. One thing I missed. I think I had mentioned something about a mean. There are contexts where it's used, but for this particular context, right, the focus here usually is you have your Y. So this is in this particular case, this is your Y1, Y2, Y3, Y4, Y5, Y6, Y7, Y8, Y9, and Y10, right? But in this particular, for this particular case, and then what happens is you now predict your Y. Where is this is your Y, and this dot predict, right, is the method that predicts it. Now, so you have your Y and you have your Y predict. I think your Y predict is your Y hat, and this is your regular Y. And then it does the same thing I described earlier, and then that's why you're able to get your R squared and then your mean squared error. Same thing. But then all you need to do is just enter this and enter this, and then you get your results. So essentially all you're doing is you're saying, this is my predicted, this is my value, this minus this will give me some kind of error. This minus that will give me some kind of, this and minus that will give me some kind of error. Because eventually your goal is for the error to be equals to zero, even though it's never really equals to zero, but then you can tend towards going to zero. We good? Let me see. Someone is trying to say something.
Yes, sir, it's clear now. Thank you,
Right.
sir.
All right. So, um, so what we are doing today is the second part of the predictive modeling thing. And part of our focus today is going to be to distinguish between classification and clustering task. And then we're going to implement classification algorithms such as logistic regression. I think we did a bit of logistic regression, if you remember something like this. Sorry. If you remember something like this from last week, let me see. Logistics regression. Yep, this, right? And what you're using is your sigmoid function. I think last week I told us about the different kinds of functions and what they do, and so you can have a range of numbers, but you can decide to squish them, right? Which is literally compress them to a range of values, say between, in some cases, is -1 to 1, you know, or you're going from 0 to 1, that kind of thing. But notice what's happening here. All your data points fall on a line, and then these other data points fall on this line. That's why you are able to use logistic regression for this. So, what am I missing here? Okay, perform on unsupervised clustering using the k-means and visual cluster patterns. Then evaluate classification models using appropriate matrices, right? And then we understand between the trade-offs between precision, recall, and accuracy. That's what I was mentioning the last time, because now you're going to have the whole thing about F-score. F-score is actually related to the precision, recall, and accuracy. And this is really very important in trying to understand the accuracy. Would I call it accuracy? In you being able to assess a model. So, as an aside, before I dig a little deeper into what we have there, right? One of the things I like to mention is you're going to see something about parametric and non-parametric models. Now, remember in week 4, one of the things I mentioned was that here, sometimes you have to update your model, because just because you built a model doesn't mean that that model is going to be perpetually correct, which brings me into the concept of parametric or non-parametric models, right? And what exactly are parametric models? Now, you can think of most machine learning models, right? They actually have a range of complexity, right? So a parametric model is one that assumes a fixed form or function for the model. It learns a finite set of parameters from the data. Once trained, the model doesn't change its form no matter how much new data you give it, right? So that's an example of a parametric model. Just giving it additional data doesn't necessarily change it, right? The complexity of the model is fixed. It's determined by the number of parameters, not the amount of data. So those kind of models, are essentially, you would refer to them as they are less sophisticated machine learning models. But the non-parametric, right? They make fewer assumptions about the data distribution. They grow in complexity as more data is provided to it. and they store part of or all of their data to make predictions. So non-parametric models are actually more flexible than parametric models. And what tends to happen is for non-parametric models, the more data that you give to non-parametric models, the better they become, which is this tends to happen to more of the more complex models. Um, so we're looking at, for example, classification and clustering. These are other predictive modeling tasks, especially for the focus of this particular week, right? So this is classification. I think we talked a little bit about that, but it's a type of supervised learning problem where the output variable is a category. So you have spam or not spam, when people send you spam emails, right? And then sometimes they create these spam filters that you can use where the system is able to catch certain characteristics indicative of spam mails, and then it will just filter them off from your email box so that you don't even see them. So it just sends them directly to your spam folder. And what's going on there is simple classification. So these are other examples of classification, disease diagnosis where you're trying to discriminate between one disease or the other. And what are you looking at? You're probably looking at some of the symptoms. That's essentially what doctors do most of the time, where you present, and once you present, they ask you questions about the symptoms you're having, and then they take blood samples and all of that. And all they are trying to do is to use those features, quote unquote, those columns, right, to be able to predict what the specific disease condition you have is, right? And all it does is segregate between a given set of disease options. Clustering a little different, this is a supervised learning problem because initially you need to tell it, for example, if I'm going to create a model that separates good emails from spam, I need to be able to give it examples of spam emails to be like, okay, usually, these are the kind of things that you can find and that you can find in a spam email. And the more and more information I give to it, the smarter it becomes, right? So that's why it's supervised, because you are essentially giving it everything it needs to know. It learns from that, and then it can make its own prediction in the future, even when those answers are not given to it. Clustering completely different, right? Where it's unsupervised learning, and I think I did mention something last week where I said think of bringing a couple of kids into a room full of toys, but then these toys, some are round, some are square, some are triangular, and then you ask them to sort all of those things out. It's possible, for example, to sort all the round balls in one bucket, put all the square ones, and how they are able to do that. You don't even tell them, you just say sort these things, right? And they will just go do it, right? And what are they looking at? Probably they are looking at the color or they are looking at the shape, right? If they decide to go with the color, the clustering will be different than if they decide to go with the shape and all of that kind of stuff. But you don't need to have trained them to do that before. Just by seeing the differences between the various toys, they are able to do that. So that's what we have going on here. Clustering, exact same thing that happens. And that means you can use machine learning, for example, to do customer segmentation, image compression, and document categorization, right? All of those you can do with clustering. So um, two other common algorithms, right, which is for predictive modeling, which is what we are focusing on today, is classification, which is, and some examples are logistic regression that I just showed us in week 4. There is KNN, you know, there's decision trees, there's random forests, and support vector machines, right? Those are all examples, and all of them, as you can see, their key characteristic is that they are all supervised learning models. And then you now have clustering, and these you can see below the examples of clustering. Even though we are just going to focus on k-means for now for the clustering, and all of those clustering, right, are typically unsupervised because they really don't need to be supervised. All they need to the system needs to do is to be able to, go through all of them and identify unique patterns or features, right? And then like kind of separate them into boxes based on those findings. So that would be for clustering. So logistic regression, right, which we already touched on before, um, it models the probability of a binary outcome using sigmoid function. If you remember, I was talking about the sigmoid function last week, right? Where, you know, you're kind of, if you have a whole set of data, say 1,000, say 0 to 1,000, you can actually squish all of that, into a narrow band of 0 to 1, right? That's what's happening with a sigmoid function. And as you go into neural networks and all of that, you're going to see the use of sigmoid function like increasingly so as we proceed with that. So where are we at now? So I already mentioned this. The output is usually a 0, a 1, or based on a decision threshold, right? And then supervised learning, what it does is it classifies inputs into binary or multi-class outputs. So one of the projects that we said we are going to be working on, the NVIDIA certificate, you're going to see a lot of things around binary classification, and you're also going to see multi-class classification there. So how it works is essentially fits a linear model to the data, and then it now uses the sigmoid function, or what you also call the logistic function, to output the probabilities. So you have, like I mentioned, right, data from 0 to 1,000, right? And then when you run it through the model, you get an output, but that output comes in terms of the probability of something happening, or the probability of that output being correct. And that probability is going to be from, say, 0 to like, because if you have different probabilities, when you add them up, ideally they should give you 100%. Now that 100%, you can now convert it, to numbers between 0 and 1. That's what your sigma function helps you do. And then it helps you, the correct prediction will now be the value with the highest, the higher value within the sigmoid function, or we would say the one with the highest probability. So logistic regression is parametric. Remember when we talked about parametric, and works best when data is linearly separable. And then you have your k-means neighbor. Your k-means neighbor is non-parametric. It classifies is that classifies based on the majority class amongst the k nearest samples. Now, I put together. I have a video that actually walks you through how that algorithm works. But in very simple terms, right? What you tend to have, what tends to happen is you have what would you call it? A couple of clusters that already exist. Let's say those kids, right, that I mentioned have come into that place, right? And one of the patterns they've identified is the shapes of the materials, and then they decide to sort out all of those toys based on their shapes, right? So k nearest neighbor, you know, what it does is you you choose a k, right? And then once you bring, let's say you introduce, now after they've sorted it, right? Now you know what each of them are, right? And you label it. Let's say this is square toys, circle toys, blah blah blah, and then different toys. Let's say we have even 8 different categories of toys. Now, that's what now makes it, at this point, it makes it supervised learning, because now everything has been labeled, right? And then you now all of a sudden bring in a toy and you're asking it to predict in which group one of those toys will fall in, right? That's actually what K means neighbors does. So there are a couple of ways, right, that it tries to predict where the toy is going to, because it's assumed that every toy, where a toy is, right, is has some kind of proximity or proximity to the group to which it belongs, right? So there's something you call a Euclidean distance, you know, which is one of the inputs or factors that this particular algorithm would use to determine which group it is in. So it does some kind of, almost like your Pythagoras theorem, to look for the shortest distance um, between the object you're trying to predict and each of the clusters. And then it decides, I think it decides, the shortest distance to that particular place. And then at some point, you can do a majority vote where you check certain factors to see which of them is better. So, not going to dwell a whole lot about this, because I already put, I think it's like an 8-minute video that walks you through with diagrams, right, of how this algorithm works. But again, at the end of the day, all it's trying to do, like I did mention, given a certain number of already labeled clusters, how do I determine where a particular toy is going to belong? And it does that very easily and efficiently. So, and then we have your decision trees, right? Um, Decision tree is essentially same thing that we all do. I have a node. Let's say I have a node A, right? And then I have a condition. I'm like, um, and let's say my node is a point in my journey, and I decide, should I turn left or should I turn right? And then based on certain conditions, if you turn right, right, and then it will ask you, should I turn left or right? Right? That's how this um, decision trees model works. Again, it's a supervised type learning, and then the goal is classification or regression using decision tree rules. Now, don't be confused when I say it's classification or regression. Now, it depends on what it is trying to predict, right? If it's trying to predict, say, because you can remember the example that we gave about emails, right? Where we say spam or not spam, right? Now, that's one level on that in the classification tree, spam or not spam. Then you can go down there. If it's spam, you can give another set of condition, delete or not delete. And then under uh, don't delete, it might give you a couple of options of things to do, right? So you're just following that tree down based on what is decided, based on the rules, which is what you see here, right? Where is it? Your decision rules, based on those rules. Now, for something like spam or not spam, right? Of course, what is it going to be? In that case, it's going to be a classification problem for the decision tree. But sometimes if you're dealing with numbers, right? Where it's not about yes or no. Then all of a sudden that this specific decision tree is a regression problem. So it depends on what kind of problem you're trying to solve. But again, for each of this, you would have short videos that you can listen to, which would help you understand the behavior, how the algorithms, and if you do some research, you would actually see the algorithms themselves, because think of it, all of these are literally algorithms, step by step way of getting to solving a specific problem. And then K means cluster. I think I did mention this last week, and notice that it's unsupervised learning. So the description that I gave earlier, you know, where it's unsupervised learning, at that point, nobody knows what's in that room, right? The system just has to try to create those groupings based on patterns. That right there is your K-means clustering. So unsupervised learning, you discover groupings or clusters in unlabeled data. And that's where deep learning actually becomes very important. And the thing with K-means clustering is computationally more intensive, because the system doesn't have any kind of answers. It just goes through to try to figure out the answers with no rules, no direction. So it's not a classifier, but you can be used to exploit data, reduce dimension, and pre-process for classification. So I think this we can talk about this when we get back from the break, because so remember I was talking about precision, accuracy, precision, recall, F1 score, confusion metrics. This is a very important topic which we would encounter even more. So when we get back from the break, I think I will have to look for a slide that I can use to better communicate this to us. Binary classification with logistic regression. So this is an example of an implementation here. So let's look at this, do a bit of a deep dive. By this time, you already understand NumPy, Matplotlib, and why we're downloading all of this. And this is for your scikit-learn. This is the package, the um, Python package, right, that is used for machine learning. So all of the tools, you know, that are required to run some of those models that I just mentioned here, right? This is where you find it. Scikit-learn. And if you want to know some more about scikit-learn, right, go to week 0. There's a video there that discusses extensively about this machine learning package. So there are different things that it calls. Instead of downloading everything, it calls up different things, right? The data sets, make classification. I think this is one of the methods for doing classification. Then it downloads the linear model. It also imports the logistical regression model. And then it imports a couple of other things, right? That you need to do your confusion metrics, which is this is your confusion metrics, right? This is one of those things that you use to evaluate your model that I mentioned, which we are going to talk a little bit more. I don't want to just gloss over it. But in simple terms, right? Precision is essentially what are all my correct positives, right? If you ask your machine learning model to predict stuff, right? You can get all your positives total divided by the total predicted positives. Recall is all your current positives and total actual positives, on and on, right? And then you have your M uh, F1 score. F1 score is actually some kind of harmonic sum of precision and recall, right? And then your confusion matrix, I think we've seen a confusion matrix. It's like the table. There's one of these tables that we see. It's like a checker table. But we will discuss that and I'll show us what each of those mean. But that's all that is being downloaded here, right? The methods so that you can. So essentially, you've gotten all of your tools that you need to be able to do a specific analysis. And then next thing it does is that it imports Seaborn. If you remember Seaborn, Seaborn is literally like matplotlib, just better, right? It helps do deep um, analysis and then an output of visualization for whatever it is that you are doing. So it's a visualization package or tool that you can call up from Python. Okay, I think that's so if you when you get the slide, this is all the explanation of what I'm trying to talk about here. NumPy for numerical operations and data manipulation, matplotlib for plotting graphs, make classification to generate a synthetic data for binary classification, logistics regression, the model from uh, scikit-learn, which is the machine learning model, and then it's used for logistic regression, and then your accuracy score. These are all confusion metrics, particularly for evaluating model performance. And then these are all the other ones, right? But the thing about confusion matrix is that it subsumes all of this. So you can see this is your true positive, false negative, true negative results. So it kind of puts them on a chart so that you can see what's going on with your model. Now, the first part of what we do here is we're generating so we don't have our own actual data, but we want to just use Python to generate a couple of um, generate some kind of synthetic data, right? So we assume we have 100 samples, so data points, and then for features, we decided to go with two features, and the idea is to help us with easy 2D visualization. So that will tell you when you have three features, right? You go get something like what we have here. Yeah, this is three features. Your X, your Y, and your Z directions. This, and this. That's I was trying to I have to run it again to be able to move it around. Yeah, not running it now. But this is just your 3D. So my point is if you have, which is what makes machine learning beautiful, if you now have um, this is 1, 2, 3 dimensions, and that's what you have here. Your regular pictures, this is your 2 dimension, this is your 3 dimension. The question will be when you have 3 features, 4 features, 5 features, how do you represent that? That's the whole point of machine learning, right? Because now even some of the things we cannot correctly or even meaningfully visualize, right, can be done with machine learning. And instead of having your regular matrix, what you now have is a tensor, right? So you have, a rank 0, rank 1, rank 2, rank 3, up to rank whatever, infinity tensors. Um, so you have all of these, but essentially what you do here is you're generating, okay, that's an error, and the error is because I haven't run this. Make classification is not defined. It's supposed to be defined here. Let me see. It's supposed to be defined here. We defined it. Where is our make classification? This is our make classification, so it's defined. Why is it saying it's not defined? Okay. So the next thing we are doing is now to visualize the data, right? You run the data here, and then that's what you have. So this is a case of classification. And what did we do here? We generated the data, and then the next thing we did, all of this is just for your visualization, right? It talks about what the figure size will be, and then um, it tells it the scatter, let me see, blah, 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 equals to y is equivalent to, this is what we call, remember when we were talking about the encoding, right? This is what we are doing with the encoding, the 0 and the 1. And then this is your title, your label, to give you your labels, the legend, and then we want this grid, and then this is for making the whole thing visible. So let me see our plots. Just 1 minute. Let me just do something. So this generated our X and our Y. So when X, Y is equivalent to 0, 1, 2, X equals to 1 minute. So this is step 1. So here you're calling up all of your data from, because we had 100 data, sample data. So the colon here just says everything in that, what do you call it now? Everything you have in your, every single data, the colon, and this, see, this is just 1, and this is 1. This is step. If you remember, for those of you that were taking the Python class with me, everything from the beginning to the end, everything from the beginning to the end. Same thing here, from the beginning to the end, from the beginning to the end. So it takes all of that data and then it plots it. That's all we have here. But what I'm looking for here now is your classification. This is, you use that to get all of the data sample, 2 features, cluster by size, 1, random states 42. And this is just for you to be able to reproduce the same results. And then, so the step 3, it just prints it out. The step 3 is now when we try to do a bit of the logistic regression. So all of this creates the logistic regression objects, and then you try to feed the data against the X and the Y. And this is how we get our predicted. Remember, I think in 4, when we were doing it, right, we've created our model, and our model is the logistic regression, which we called previously. And then what we are doing here is to use the dot predict method, right, to predict our Y spread. And then the next thing we do here is to be able to get the values we've gotten here. What's the probability, which is the model dot predict probab, gives class probabilities, right? Extract probability for class 1. And we're looking at the probability there, and then we evaluate our model. So if you evaluate your model, this is your confusion matrix, and it's predicting an accuracy of 1. And this is not very normal that you have a prediction of an accuracy of 100. But again, we don't have a lot of data, number one. And then number two, that data is synthetic data, right? So what this does here is it gives us our confusion matrix. And this is how you do your confusion matrix. Remember, we have our y, which is the actual value, and then the predicted value. If you run all of that, you get your confusion matrix. So sometimes you might have, depending on, and we have like 2 columns and 2 rows here. Why? Because our number of features is just two. You can have 100 different features, and then it will give you some kind of square where you have 100 rows and 100 columns. Then we visualize the decision boundary. This is all we're all most of what this does is essentially just creating the boundaries for us, but we already have this before. So this is not necessarily too important, but then it just helps us. All this story here is to be able to help predict, put the colors, separate the lines and all of that. Now, remember we got, what did we get here? We got probability, our probability here, and then we want to squish all of that now using our sigmoid function, which is our sixth step. And that's where you go use your sigmoid function. Notice where they put it here, right? Plot. Xvals. You're creating a line, and then this is your sigmoid function. And then you run all of that, and then that is where you arrive with your answer. So this is how it's all of that data from the beginning to the end. This is how it's squished. So the next thing we have is also a second example of binary classification. But if you remember, this is, what do you call it now? The data about a flower where you have the length of the sepal, the width, the petals, and all of that. But we're now trying to, before we were using this in synthetic data, but then let's try to use this actual data. Now, we already know what all of this is, right? Seaborn, matplotlib, the logistic regression, which is our main model for binary classification, the train tests split. This would help us split the data into training data and testing data. So what's going to happen here? It will help us split it, and then it will keep one part of that data so that after we build the model, we can actually use the test data to test whether our model actually works. So to do that, let's run this. Let me see. Okay, so this is all the same thing that we did before, where we are just calling up. Now notice this point. This is where we load our iris. The data is actually just called iris. It's a very popular data set, and I think we've used it a couple of times in the class. So this is our data set here, and then we try to print the first 5 rows of that data, which is this. We display the head 5, and then we try to for else 0 binary. Okay, we want 2 targets, right? And then because we are trying to do a binary classification, and because we are trying to do a binary classification, we have set, let me just run this. first. So notice the species, right? There are so many species here. And this is one of, let me go do the tail first. Let's see what appears at the tail. So you see, this is a different species. Virginica, this is a different species. But the species we are working with here is the head. What did I just do? Oh, head. So we're saying we're trying to make this our target. I don't know if you all still remember what our target is, right? When we're looking at the data for the house. So we have all of these as our features, but this is what we are trying to predict. What we are trying to predict is what you call like your target. So the iris target is equals to the species, and we want that species to be equivalent to this, right? And that's what we are trying to predict. So essentially, when we are doing this binary targeting, we will say since we are trying to predict setosa, we'll be like, we are trying to tell the system, hey, if what we are predicting is setosa, which is what we talk about in coding, binary encoding, if what we are trying to predict is setosa, then the value should be equals to 1. But if it is not, then the value should be equals to 0. That's essentially what we are trying to do here. So, but we start by trying to figure out, okay, let me just run this. So notice what's happening, right? When you run that classification right now, what did we notice? Class classification target. So for 0, and what is our 0? 0 essentially means that what was predicted is not setosa, is equals to 100, and those that were predicted to be setosa is 50, right? So it loads the iris flower data set. So you have 150 samples, and then there are 3 classes, right? And the 3 classes are Satosa, Versicolor, and Virginica, right? So for one, like we mentioned earlier, if it turns out that it gets 1, that means it's Satosa. But if it is this or this, then our answer is 0. So when it ran that, we got all of this. So we've been able to get that. So the next thing we want to do right now is to split the features and then labels. So this is what we have. X is equals to iris.drop, the target, and then your Y is equals to the target. And then we run. So this is random 42. And when you use random 42, you are just trying to make sure your data stays fixed. And then you can decide on your test. All of this, right, is essentially used to help you split the data. So you have this, you have this, you have this, and then your Y test is equals to be beginning from this point to this point is your Y test. And then your test data, you can decide, I want 70% of that data to be for training, and I want 30% of that data to be for testing. And that's why you have the 0.3 here. You can decide to change it to 2 or 1, but I think 7 to 3 is a good proportion, right? So which is what's explained here. Data is split into training 70% and testing 30%. The satisfy Y enables balanced class distribution in both sets. That's what this helps you do, because if you're splitting it, you want some kind of proportionality of all of the data sets, right? Of the various uh, data types, right? To for some of it to be in the training data and for some of it to be in the testing data. And that's what this helps you do. Random underscore state equals to 42 ensures reproducibility so that the same split, for every run. And then this is where you train your regression model. Again, this is what you use to train it. Did we run this? Yeah. And then this is where you make your prediction. So the model predicts class 0 or 1 for the unseen test data. It tries to predict whether a flower is setosa or not. Like we described earlier, these predictions will be compared to the actual labels, right? So this is the 30%, which is your Y test for evaluation. It returns a list of predictions, either 0 or 1. Note, the predictions are made after training and are used to assess how well the model generalizes. So this is all about your confusion metrics, if you remember what we were talking about. And this is an example here. And this is a binary situation, right? It's either it's a Satosa or it's not. So it's not a multi-classification problem. This is a binary. It's either Satosa or it's not, right? But all of this is just essentially your confusion metrics and some of the classification metrics, your accuracy, your precision, your recall, and then your F1 score. And I mentioned that your F1 score is gotten from your precision and your recall, both of them, because this is a harmonic sum of the precision and the recall is what gives you your F1 score. And then all of this is just printing out the results that we've gotten from all of this place. And all of these are important to know. And I'm not saying cram because these are just like methods within Python. We just call them, but everything is hidden in some function out there that has written the code of what it should do, right? And then that's how we arrive at this. So we can see that the accuracy is 1, the precision is 1, the recall is 1. Now this is crazy. Yeah, in an actual large data set, right? You wouldn't be getting results that are so seemingly super accurate. That's not how it works. So overall, these are the performance metrics. Overall correct predictions is your accuracy, precision, correctly predicted positives. I already talked to us about all of this. What's accuracy prediction? So that's what we'll look at later. And then we want to visualize the decision boundaries. Um, this is supposed to show, it's not showing. Not sure. But you have show here. Okay. Not sure why this is not showing, but it's supposed to show, and it doesn't even give me some kind of error. But again, this is not the very important thing. The most important thing is actually this, where it's able to tell you what's going on, and what it's able to predict. All right. So what time is it? 10:31 my time. I guess we take a quick break. Okay, let me just finish this and then we take a quick break. So clustering with k-means. Remember we talked about the clustering with k-means, right? So what I've done here is I've written all of these functions. This is what do we call it now? The syntax. So when you have your k-means, right, this is the syntax for it. But I think the most important thing here is the number of clusters. That's the most important thing, right? And usually the clusters, you have to randomly choose how many clusters. So this is an example of what we have here. And it's still using that same data, right? We have all of this here. K means number of clusters 3, random states 0, K fit features, and then you run this, and then that's what we have. So you notice how it clusters all of the data in different places. So when it comes to implementation, very easy to implement. And that's why, again, I mentioned that I'm trying to focus on this. And again, you don't have to write any fresh code. You just need to be able to read the code, understand what's going on, and then you load your own data. And then, of course, you want to find out what are the specific things. So, for example, here it just talks about the specific features I'm trying to see, my length, which will completely be different from any other data that I'm working with. So again, the important thing is uh, look at, because these are all existing algorithms. A lot of these algorithms are developed by some professor or some research group, right? That, has worked on that problem sometimes for years, and then they have it. But you need to be able to get the algorithm, understand, first of all, which those videos will help you do is understand what the algorithm is actually doing, and then you can always get existing code. And then the third part, which is the main thing that you're supposed to be doing, is if you understand the behavior of the algorithm, what it's trying to achieve, and then you have the existing code, you can now modify that code and then do implementation of that code to test whatever it is that you're trying to test for these models. So these are some additional materials that you can study alongside with what I have here. And these are some problems you can try on your own if you have the time. I know it's a lot of content, but even beyond this class, my hope is that you have all of these materials that you can use on your own. So let's come back um, 10 minutes before the next hour. 10 minutes before the next hour. So that will give us like 15 minutes break. So I don't know what time it is, WAT, but for those of you in the Eastern time, right, we'll come back by 10:50 to continue. And then if you have any questions, feel free to come bring those questions once we get back. Thank you. Yeah, so we are back. I know we've had some backside conversations about some of the ideas around recall, precision, F1 score, and confusion matrix, where we talked about recall being true positive all over true negative plus false negative, precision true positive divided by true positive plus false positive, and F1 score, which we said is the harmonic mean, right, of recall and precision. And the idea is that F1 score actually captures some of the really important things about recall and precision, right? And that neither of those factors, precision or recall, can effectively stand on their own. When you are evaluating a model, that's the reason why you have the F1 score. So the other thing I did mention was that your recall and your precision are often they are often complementary, and then that the precision focuses on trying to figure it's about efficiencies, trying to figure out you know the all of the positives, but recall also looks at the positives, but more from the label side. And I'd also mentioned that I will try to see if I can put together additional materials, probably record a video that I can use to supplement this, and also put in some videos that you can watch on the subject. But and I'm kind of flogging through this whole thing because I think this is a very important topic, and that's why I'm going to do what I'm going to do. So that's where I would drop the issue of accuracy, precision, recall, F1 score, and confusion metrics. So I'm going to continue with what we were doing the last week. And for those that are not here, beginning on, let me see, 16th, 23rd, and 30th, we're going to be focusing on, working on some models, some of those NVIDIA models, but a lot of the ideas that are being canvassed and discussed, right, will be what we'll use to work on that specific certificate. So please get ready. If we can, if you can, make accommodations for that day that we might run a little later. So that would be it. So this the what you have on your screen is a follow-on of what we were working on the last time when we talked about all kinds of things, right? But now we're talking about loss functions. And let me go at the heart of many machine learning models, especially linear models and neural networks, is the idea of weighted sum. We have talked about the weighted sum and all of that, right? So a loss function is a mathematical function that measures the difference between the model's prediction. We did talk about that earlier today. So the model has its own prediction, but there is an actual value which we know. And the loss function is essentially the difference between both of them, right? It outputs a single number, and that number is the loss and tells you how bad the model's predictions are. So the goal of training actually is to minimize that loss. Every time we are training, we are trying to get a better prediction that comes that equals to that would such that when you subtract the prediction from the actual value, you will get a zero. It doesn't always happen, but the idea is that you tend towards zero. So whatever that delta t is, right, the difference between the prediction and the actual target is what you essentially call your loss. Now, what's the role of a loss function? The model makes, say, a prediction of y hat. You compare it to the actual value. This is your actual value, your y. So that loss is how wrong this is, your y hat, which is your prediction. In other words, the difference between this and this. So we're trying to figure out how badly this guy damaged it, right? If this is 4 and then this is 6, you know that this one is off by 2, right? So that we are trying to figure out how off is that y. So how do we do that? We now adjust the weights to make the next prediction less wrong. If you remember when we were talking about our weights, right? The idea is we adjust this weight because at the end of the day, we are going to predict something. Being able to work with these weights well, right, is what's going to determine your result. So, um, So somebody asked the question earlier about mean squared error, and this is your mean squared error. That's your predicted minus the actual, right? And then we square it divided by 1. That would be an example of your mean squared error. But like I said, because we are squaring it, you're going to penalize large errors, right? Because anytime, so if I have 2 squared, I'm going to get 4. If I have 3 squared, I'm going to have 9. But if I have 100 squared, then you can see how large that is, right? It's like it's going to be 100 times 100, right? Which will be huge compared to 2 squared will be 4, 3 squared will be 9, but 100 squared, right, will now go give you 100 times 100, which would be like something like 10,000, so it really penalizes large errors. So mean absolute error, it's still 1 over n, but it's absolute because sometimes, like in the previous example I talked about, right, the prediction was smaller than the actual. So it's going to give you, say, let's say this is predicted is 4 and actual is 8. It's going to give you minus 4, right? But to get mean absolute error, you have to take, what do you call it now? The absolute
Well,
value. Yeah, the absolute value. So that instead of being minus 4, it will be 4. And then you divide it by the total number of, and that's how you get your. So the way mean absolute error behaves is that it actually treats all errors equally. So beyond these errors, which is something you see in regression, right? Now, but when you go into classification, you also have those errors, right? But the errors are crafted mathematically in different ways because conceptually, right, they are not exactly like your linear errors, right? So this is the formula, right? When you have two classes like spam, spam, not spam, or yes or no, right? Or I'm trying to discriminate between a dog and a cat, right? What I'm doing is binary what I'm going to use is binary cross entropy. That's for two classes. And this is what it is. It's actually very simple. Forget about that. It's looking esoterical mathematically, right? But all you're just doing is you're taking your y value, which is the value that we know that is correct. You take the log of the predicted value plus 1 minus the true value that we know to be correct, and then you do the log of 1 minus y. So if you look at these two things, right, all that is going on is the only thing that changed here is we put a 1 minus y, 1 minus, and then here you do 1 minus because it's just y log y hat. So this is the literally a complement. So it's used when output is a probability. And remember, when output is a probability, right? It's either 0 or 1. That's why you're using the sigmoid output, right? So cross entropy is usually used when um, you know, that your sorry, binary cross entropy, is usually used when there is a binary situation, and binary just means two. There are two classes, but you see there's a way to actually minimize this equation that it becomes easier to look at. So for categorical cross entropy, right, that's when you have more than two classes, right? Same way that you use these for classification of linear models, right? Particularly linear models of the regression bent. That's how you use these for. So beginning, was it the 16 that I mentioned? When we are going to do that, I think there are aspects of it, right, where you're going to be looking at binary cross entropy, you're going to be looking at categorical cross entropy. And you can tell that binary cross entropy is always used for two classes. Categorical cross entropy is for more than two classes, right? And there's something called soft max output, and I'm going to talk to us about it later. It's used when predicting one of several classes, right? That's what you use the categorical cross entropy for. There are more than two classes, and it's used when you're predicting um, more than two classes. I don't know how much time we have, but let me just quickly finish this. And next week, I think I might spend some more time digging a little deeper into some of the machine learning. And I'm also going to create one folder where I'll just drop all the things around neural networks and all of that. When you have time, you can look at it. It's really good videos that can be helpful. So binary cross entropy is one of the most important loss functions used when a model is performing binary classification, where each prediction is either yes or no, true or false, one or two, spam or no spam, dog or cat, closed door, open door, all of those kind of things that are straight up yes or no. So, and I talked about this is what we have here. That's the formula, you know, and Y represents, the true label that I talked to us about, and this is the predicted probability, right? And categorical is for, and by the way, you have these slides already. I put it there last week. Is a call loss function for multi-class classification problems in machine learning and deep learning. CCE, which is the same thing as categorical cross entropy, is used when you have one correct class per sample. You have one class, but then there are several classes that you have to interact with, but you have one class that is the correct answer. So the predictions are from soft max. So what happens is you get your probability and then you apply. I'll show us. You apply a soft max. I think it's an algorithm, and it will convert everything right so that when you add up the sum of all of the probabilities of each of them being correct, the sum will give us a one, right? So, categorical cross entropy measures how far off the predicted probability distribution is from the true distribution, which is usually a one hot encoded vector. And I talked to us, I think it was last um, class when I talked about the one hot coded vector. So, what categorical cross section measures is how far of the predicted probability distribution. So, it's a distribution, right? So if you have like five different things and only one of them is correct, what you're trying to do is you want to assign probabilities to each of them to say, okay, this is the correct one. So this might be 10% correct, um, 20% correct, 60% correct, blah, blah, blah. Now, because 60% is larger than all of them, 60% is the correct answer in that particular place. But then what it does, categorical cross entropy, is that it looks over that entire distribution. Um, oh, remember I mentioned that you can actually squish this formula down, right? This is actually what it turns out to be, right? And C, you can actually take a summation of everything. Let's say there are five of them. You take a summation of them, right? And this is what you have. And then where C is your number of classes, yi is if class I is the true class. I said one to five, right? One of them might be the true class and the others are not the true class. Then when you apply one hot encoding, remember that I told you that, then all of them, right, will be zero, zero. The one that got the 60%, because it's higher, it will be one, or the other ones will be zero, zero, zero. That's what it is. So because y is equals to one, only for the true class, the formula simplifies to this, right? So this automatically simplifies to this. Why? Because when we run the one hot encoding, right, only one of them is going to be correct, right? And if you run all of those, right, your y in this case, if we have a situation where one is zero, the other one is zero, 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 the only one that will survive is the one that is one times this. And that's where you get this, right? Let me see. Time. I think we are way beyond time. So I'm going to stop. Maybe I'll come back here and we talk about this again next week. Maybe that's one of the first things we do. And then I will show you some examples, very intuitive examples of how it works. And then we'll continue with the class next week. But sorry for taking so much of your time. We'll continue next week, except if someone has a question, comments, and all of that. And please remember to keep working on your project, because somewhere along the line, I think I'm going to. Uh, Hmm. Okay, I couldn't do the pool around. I couldn't do the pool around the people that said they missed the test. So I'm probably going to send it to the group or the class, and then um, once we finish with that, whatever the answer is, please, those that still need to take a test, email me. But depending on what the class decides, we will now go from there. All right, guys. I shall see you all next week. Keep the faith. We're also going to, please, everybody, every group, please keep working, because very soon you're going to have to come present, and it might be randomly. So look at the deadlines, look at the dates, because you might have to be called up to come present your whole thing to the class. Mr. Jimo, your hands are up, sir. Okay, it doesn't seem like he's.
Okay, hello, sir.
Yes, sir.
Yes, I have a challenge. I for the class test, I did all the tests before the time and I submitted and even viewed my scores. But I'm surprised that